We're going to look at how Softtree software can be used to analyze cable harvest planning for forest operations, in particular with cable yarding and steep terrain. So logging in steep terrain requires planning, and the selection of the harvest system and the placement on the terrain influence the financial and the environmental success of the operation. In case of cable yarding, proper positioning can make the difference between high production and low costs, and sometimes not even being able to harvest a unit because it simply doesn't work. There's safety involved and production rate. It's important to put your yarders where they should be, and to build the roads. They're expensive too, in the best place possible. So we need to bring in some surface data to do good cable yarding. Luckily, we've got LiDAR. LiDAR can generate a 3D surface quickly and relatively inexpensively, at least for large areas. And at least it's expensive per unit, per kilometer squared for large areas. And our software allows you to create cable harvesting analysis pretty well anywhere on your surface. And that can help you find landing sites, and we'll show you that. We'll also show you the possible outcome of your analysis. We can take this data into the field, and that will be the end of our presentation. So let's take a look at LiDAR first. Comes in tiles. Usually they're about 1 kilometer on a side, less than half a mile, and they're dense. There's a lot of data in a LiDAR tile. The data sets can be enormous, especially with high resolution data. We don't need particularly high resolution for cable analysis, at least not in modern terms. 1 point per square meter is just about all you need. And that's probably good enough to do roads as well. So when you're bringing in huge data sets, you need to be able to, first of all, choose where the data comes from, so you don't bring in data outside your area of interest. And then you may need to thin it down to make the data set manageable. LiDAR is generally created from an airborne platform, a plane, a helicopter, sometimes drones. And the data accuracy is on the order of about a decimeter, 10 centimeters, a few inches, plus or minus, and that's in both the X, Y, and the Z dimension. The other great thing about LiDAR is that it's now available in a lot of public sites, government-sponsored sites, and it's free. And you can, so if you're lucky enough to be in the right area, you can download LiDAR without paying for it. Here's a few places you can get publicly available LiDAR, and you can check Softree's website to find a few of these links. So LiDAR is relatively cheap, at least per square kilometer or per area. As I mentioned before, you can get accuracies up to about a decimeter, and areas can be huge. This is a blessing and a curse. The fact that you can get multiple harvest areas in a data set means you can do long-term planning. And if the data is managed properly, this can be very useful for looking far in the future and designing roads and landings from the office without a huge amount of manpower on the ground. So the software that we're going to look at allows you to explore deflection on your terrain. You can also analyze payload and clearance and line tensions if you need to. Honestly, most of our customers just look at deflection. They're just looking at the shape of the terrain, where's the best place to put the landing and the tower. and analysis you do once or twice just to confirm that things are going to work for your machine, and then you do a lot of deflection analysis. And you can try different configurations for different areas. So if you have multiple yarders, this can allow you to choose which yarder works best in which area. And then you can generate output for documentation, for directing the people on the ground. It's possible to take the data out into the field. Everything can be georeferenced, and that can speed things up. So first, let's take a look at the well, the workflow. I guess once you know what all the pieces you've got, you need to get the ground surface first. Then you think about the type of logging configuration you want, what kind of yarders you have. Then choose where you think the landings should be. Sometimes the landings are well defined because the roads already exist. Other times you're looking on virgin territory and you want to know where to put the landings. And finally, you can place the deflection lines in various places and see how it looks. As I mentioned, payload analysis is something you may or may not need to do, probably something you do once or twice. And finally, generate your output. So let's take a look at the first part of this. This video is going to show the process for actually creating the LiDAR surface. So we've got some data here, mostly just an air photo, and there's some roads, and I'm going to select a road and a rectangular area. I'm going to use those to limit where my LiDAR data is read into the software. Create a brand new terrain module document and then paste those two items in there. Of course, there could be more than two. And now I want to read in my data. Now in this case, I've got LAS tiles. That's kind of the most raw form you get. But we can also read USGS DEM, which is a grid format. We can read ASCII, and we can read multiple tiles at once. I've selected 2 here. There could be 20. When you open a LAS file, you have the option to choose what kind of points you're going to read in. For cable analysis, we only need the ground points. And there's options here to select and now I'm going to change where the data comes from. So I'm going to choose this rectangle that I created before as a region, and I'm going to create another region for the road, which is a corridor. So we'll choose that feature and make the corridor width 200 meters. That's 100 meters each side of the feature. So those 2 regions will be read in without skipping any points. And then the default, that's everything else. I'll just throw away all the data. So this will limit the amount of data that we read in, the number of points we read in at read time. This is a georeferenced file. So I'm actually going to choose that as my projection so that when I'm finished, everything is georeferenced. We can export to Google Earth and Avenza and so on. So you can see there's a lot of data points read in, but only in my area of interest. This reduces the number of points. It says on the bottom of the screen we've got about 800,000 points. And you can see it's quite dense in areas, particularly at the bottom there and at the top near a road. So it's more dense than I need. And I can reduce the data further by using our simplify operation. These tiles, I don't need them. That's where the data would have filled those tiles if I hadn't used the selection methods. Okay, simplify. So I'm going to use a grid simplification. Choose a grid size of 1 meter. It puts a 1 meter grid over the data and picks 1 point per grid cell and throws away the rest. So it doesn't actually make it into a regular grid, but it removes points where they are redundant. In an area where the data is sparse, and that happens often with canopies when you're serving LiDAR in a canopy, you have sparse data sets, and the sparse areas won't be touched. So here I've reduced my data, not by a half, but almost, and areas where the data was dense, we took a few points away. Areas where the data was sparse, we didn't touch it. Now I'm going to make some contours and also make the surface at the same time. The minimum side length, just make sure we don't get any stray triangles going a large distance between points. And there is your contour calculation and surface at the same time. So that's the 3D surface. Now we're ready to do cable analysis. So in this next section, we're going to look at the cable analysis explore mode. So we are imagining here that we have a territory without roads. We just want to find the best place to put landings, and then we'll join them up with roads later. So I choose what kind of yarder I want to use and what kind of calculation I want to use. And in this case, we'll just choose a simple third point deflection where we can pick the deflection percent, in this case 8%, and then I can create as many radial D-lines branching from a point. So in this case, we're going to go up to 300 meters, 16 yarders, or 16 D-lines, and we're going to use the auto position to make sure there's always 2 meters of clearance. I've got a 5-meter tail spar, and there it is. So there's 16 D-lines, and it's showing 9.4 hectares, and that they're not all 300 meters long. It's actually chosen the end point automatically so that we've got at least 2 meters clearance along those green lines, and the boundary gives us an area. Press accept, and the deflection lines become anchored into the model, and now I can do some further analysis. Now I've chosen a deflection, pardon me, a layout that allows me to look at my profile, and you can see there's the 2 meter clearance close to the tail spar. I can use different analysis. So here's minimum deflection given load. That will show me a curve where the carriage will go if we put a 20,000 pound load on that grapple yarder. And that we'd use fixed skyline if you were doing a motorized dropline carriage or something like that. So you can do different analysis and look at what the profiles look like. And now I can choose another landing site. So we'll again enable explore mode, use the same options, and start poking around on the terrain to see where is a good landing, what gives me a good harvesting area and reaches the blocks and harvest units that I want to reach. Now imagine that instead of working in virgin territory, we actually have a built road, and the landings are well defined. Or maybe not. Maybe we need to choose where on the road we want the landings, but the road is there. So I'm going to work now by creating one landing at a time, or one deflection line at a time. With a draped feature, I can pick the start point, pick the end point, and the software calculates the profile. That's quite dynamic. So let's put a deflection line on there. Again, I choose my yarder, and I can choose also the tail position. If you just put a large number here, it will always go to the end, and the tail spar height. So now I can move that around and it will calculate the deflection as I move it. It's dynamic. The red zone is out of reach, the green is not. And I've chosen the wrong calculation. Let me just fix that. Calculation parameter should be simple third point deflection in this case. And you can see that that's kind of tunneling there, but not there. Anyway, let's pick a few spots and let's duplicate that. So now I can just copy, AutoCalc, right? We can choose the end point automatically using the auto calculation function, and that will happen. Now I'm duplicating. You can see that the features, we've got 4 of them now, so just a simple copy paste allows me to create a new feature, and then I can modify it. And then once they're created, I can go back to the cable analysis options and AutoCalc the tail station for all of them all at once. There we go. So copy, paste, move it around. After a bit of repetitive work, we get something that looks like this. You can see in the 3D that we've actually got a representation of the cables as three-dimensional lines, and I can pick any one of the features and I can see it highlighted in magenta, and you can see the profile and the three-dimensional shape as well. So here's an output sheet. We've got the finished road done in a fairly nice looking 3D with the road and the landing and the ground all accentuated with colors. And on the right we've got the multi-plot output sheet. So we've got four cables on there. There's a little text underneath each of them. That's all configurable. So you can imagine printing that or saving to PDF. In addition, rather than just show a simple deflection, we can do calculations. So in this slide we've got the cable tensions as a graphic. There's a little graph showing the deflection, the load, and the cable tensions in red at the bottom. And then you can also put that into a table. So the load is fairly boring. It's always the same in this particular calculation, 20,000. But you can see how the cable tension works. I think near the landing, it's the main line that is maxed out, and then near the tail, it's the haulback that is limiting how much higher you can lift the load. So yes, you can generate output in a PDF format. We can, of course, generate those tables, but we can also save as land.xml, DWG, text files, CSV, and export to Google Earth. Those are georeferenced lines that can be read into any kind of 3D software, including Google Earth. And Avenza, which is relatively new for RoadEng. The line work and the map can be exported to Avenza, and then of course you get a cursor showing where you are in the field, and you can walk right up to that tailhold and it'll show you, yes, you're near the tailhold, and you can start looking for a tree that might be suitable or other anchoring features. Feel free to email Softtree and ask us any questions. Thank you for watching this demonstration.